Welcome to the Deep Dive. Today, we're diving headfirst into, well, one of the most mesmerizing yet challenging frontiers of AI, the very essence of light itself. Light isn't just something that hits our eyes, it really sculpts our entire perception. It defines every mood, every scene, from a breathtaking photograph to an epic movie moment. But here's the thing, while our brains effortlessly process and interpret light for machines, truly understanding and recreating light from just a simple image or video, that has been an incredibly complex, long-standing challenge, almost a holy grail. So today we're tackling lighting estimation, this ambitious quest to accurately infer a scene's illumination. And we're going to explore a groundbreaking new technology that's, well, utterly transforming this field. LuxDiT. This is a really monumental development. It comes from the brilliant minds at NVIDIA, the University of Toronto, and the Vector Institute. And it's designed to generate stunningly realistic high dynamic range, or HDR, environment maps from just visual input. Pretty amazing stuff. Our mission today is to understand how LuxDiT is overcoming some of the most persistent challenges in computer vision and graphics, paving the way for unbelievably realistic virtual experiences and, what its impact could mean for everything from augmented reality to the future of film production. Let's eliminate this. Okay, so to truly appreciate the magic of LuxDiT, we first need to confront the monumental challenge it's solving. Why, in this age of advanced AI, has something as fundamental as light been such an elusive enigma for computers? I mean, in computer graphics, especially physically based rendering, lighting isn't just important. It's like the master artist, right?
Absolutely. It dictates everything. How objects cast shadows, how they reflect their surroundings, how truly integrated they appear within a scene. Nailing this is fundamentally key for so many applications.
Right. Whether you're, say, virtually inserting an object into a real video or
Mm.
building augmented reality experiences where digital stuff blends seamlessly with the real world,
hmm
or even generating synthetic data to train other AI systems. Accurate light is the bedrock.
It truly is.
But trying to infer accurate, realistic lighting from just a casually captured image or video, that has historically been, well, a monumental task.
It really has. The challenges are significant.
Yeah, like first, light is often a master of disguise, isn't it? It relies on these indirect visual cues.
Exactly. Think about how you instinctively know if a room is brightly lit just by the way shadows fall, or how a shiny surface reflects its surroundings.
For us, it's effortless.
Right. But for a computer, trying to decipher these subtle hints like the nuanced shading on a surface or a faint reflection has been incredibly difficult. It's almost like trying to read a story told entirely in whispers and glints.
That's a great way to put it. And second, lighting isn't just local, is it? It affects the entire scene.
Precisely. A single light source can cast shadows across an entire room, so computers need to perform global reasoning. They can't just focus on local pixels.
It's like trying to understand the weather by looking at a single raindrop, rather than seeing the whole storm front.
Good analogy. And then there's the third challenge. Real-world light isn't simple.
You mean the intensity.
Yeah, the intensity can vary wildly. From the blinding sun to a dim indoor lamp, capturing and representing this high dynamic range, or HDR, is inherently difficult. It requires recording an enormous span of light intensities.
And maybe the biggest hurdle has been the data scarcity. That chicken and egg problem you hear about.
Oh, absolutely. You've hit on the core issue there. Existing learning-based methods need vast amounts of expensive, specialized ground truth HDR environment maps for training. These are typically captured using, light probes or multi-exposure panoramas, which needs special setups.
But if the goal is to avoid needing that expensive data capture,
Exactly. How do you get enough of it to train the model in the first place? It's a real conundrum.
so what's fascinating is that current methods often struggle because of that limited data diversity, right?
Yeah,
Especially in complex, in the wild scenes.
precisely. The kind you might just capture with your phone. They might produce results that look visually plausible at first glance, but they're ultimately inconsistent or simply lack the full richness of real light.
Like diffusion light, for instance.
Yeah, take diffusion light. While it was an innovative step, it relies on an expensive test-time ensemble strategy, basically running multiple inferences and stitching them together, and it still struggles with accurately capturing the full dynamic range.
It's like trying to piece together a complex painting from many blurry fragments.
That's a good way to think about it. It really points to the need for a truly generative approach, one that doesn't just estimate but actually creates the light.
That makes sense. So it sounds like many existing solutions, while innovative, were really hitting a wall because of these fundamental data
and representation challenges.
Yeah.
That sets the stage for LuxDiT, doesn't it?
It really does.
But before we dive into its brilliance, let's just quickly unpack why this problem matters to you, our listener, beyond the technical stuff. This isn't just about tweaking pixels for some niche tech audience. Why should you truly care about a computer seeing light better? What new, maybe even mind-bending experiences could this unlock?
Well, imagine this. You film your kid's school play on your phone,
Okay.
and instantly a virtual dragon can fly across the stage, casting perfect shadows on the real backdrop, its scales gleaming with the actual stage lights.
Wow. Okay, that's cool.
Or you're an interior designer showing a client how different furniture would look, precisely lit by the sun streaming through their real windows.
Ah, I see. Much more realistic previews.
Exactly. Or think about video calls where your virtual background isn't just a flat image, but a dynamic environment that literally lights your face as if you were truly there.
Okay, that would be a big step up. So it goes far beyond just pretty pictures.
Absolutely. It's about bridging the digital and physical worlds with, well, unprecedented realism.
Well, the good news is LuxDiT is precisely that innovative solution that seems to deliver on this promise. It elegantly reframes lighting estimation as a conditional generative task, completely changing how we approach this problem.
That's exactly right. At its core, LuxDiT is a novel, data-driven approach that fine-tunes a video diffusion transformer, or DIT,
DIT, okay.
to generate those HDR environment maps conditioned on your visual input.
Now, why diffusion transformers specifically?
Good question. Think of them as like the next generation generative AI models similar to the ones behind DALL-E or Midjourney, but trained specifically for video and complex spatial tasks. Their attention-based architecture means their digital eyes can take in the entire scene at once. They can understand how a subtle reflection on a coffee cup is connected to the window light across the room.
That global context aggregation you mentioned.
Exactly. That, combined with their strong generative priors, allows them to reason from those tricky indirect cues like shading and reflections much more effectively than previous methods.
So it's not just guessing the light.
No. Essentially, LuxDiT effectively synthesizes entire HDR panoramas from noise, painting a full light map guided by your input image or video. It creates it.
That sounds incredibly powerful. So how does LuxDiT actually apply this innovative thinking to those other big challenges we talked about, like interpreting subtle cues and understanding the global context?
Yeah, where did the team focus their technical ingenuity?
All right.
Okay, this is where LuxDiT really shines with some clever engineering. First, let's talk HDR lighting representation.
Okay.
Standard variational autoencoders, VAEs, they're like the digital sketch artists in many AI models. They're great at drawing average pictures.
But ask them to sketch a scene with both blinding sunlight and deep shadows. They often get lost because of the vastness of light intensity.
Right. The dynamic range issue.
Precisely. LuxDiT's genius is in effectively taking two distinct snapshots of the light. They call them two complementary tone-mapped representations for each HDR panorama.
Two snapshots.
Yeah.
How does that work?
So there's L-Gorder. That's a standard Reinhardt tone mapping. It captures the overall brightness and midtones, like a well-exposed photo.
Okay, the general look.
Exactly. And then there's E-Log. This captures normalized log intensity, specifically designed for those extreme brights and darks. Think of it like a photo taken with incredibly long or short exposure to catch details at the fringes.
Okay, so one for the middle, one for the extreme.
You got it. These two snapshots are then seamlessly combined by a lightweight multi-layer perceptron, an MLP, to reconstruct the final, complete HDR map. This dual approach ensures sufficient sampling across the full dynamic range. No light detail, bright or subtle, gets lost. That makes a lot of sense. Very clever. What about the second point, the attention-based conditioning?
Right. Traditional methods might just sort of glue your input image directly onto the noisy digital canvas the diffusion model is working on.
Okay.
But for non-pixel-aligned tasks like lighting estimation, where the output isn't just a pixel-for-pixel translation, this often leads to poor performance.
Right, because the light isn't in the pixels in the same way.
Exactly. LuxDiT, however, uses a fully attention-based architecture to process the input visual data. This means the model isn't just looking at bits and pieces. It's intelligently extracting and utilizing incredibly fine-grained shading cues, things like shadow orientation, surface reflections, specular highlights.
The subtle stuff.
The subtle stuff,
Yeah.
with much greater flexibility and accuracy, understanding their relationship to the overall light.
And the third innovation, the directional embedding.
Yes, this is critical for realism. To ensure angular continuity in the predicted panoramas, which you absolutely need for realistic shadows and reflections, LuxDiT injects directional information directly into the model.
How does it do that?
Imagine a tiny compass needle embedded in every digital pixel it's generating. It creates a map of unit vectors encoding per pixel lighting directions, and fuses this into the noise tokens, the raw material the diffusion model starts with.
Okay.
This promotes rotational equivariance, meaning if the scene rotates, the light sources rotate convincingly with it, and it ensures robust directional encoding. So the predicted light sources behave exactly as they would in the real world, making sure those shadows fall precisely where they should.
That dual representation approach truly sounds like a breakthrough, and the attention mechanism explains how it can be so precise with those subtle cues. I'm curious, though, how do you even begin to teach a model these impressive capabilities, especially when, as you mentioned, real-world HDR data is so scarce? What kind of secret sauce did LuxDT employ in its data strategy to overcome that fundamental hurdle?
That's a crucial point, yeah. And it brings us to LuxDiT's sophisticated data strategy. It leverages three complementary data sources to get around that chicken and egg problem.
Three sources, okay.
First, there's large-scale synthetic rendering data. This is absolutely crucial for LuxDT to learn physically grounded cues for light, direction, and intensity. They generate randomized 3D scenes with diverse geometries and materials pulling from vast libraries like Objaverse and MatSynth under a huge variety of lighting conditions.
So perfectly controlled virtual worlds.
Exactly. These synthetic scenes exhibit perfectly accurate effects, cast shadows, specular highlights into reflections. They provide pristine, perfect, ground truth HDR illumination that would be impossible to collect consistently in the real world.
Makes sense. What's the second source?
Second, they use curated HDR panorama images.
Yeah.
Real ones this time. By sampling perspective crops from actual HDR environment maps captured with various camera parameters, this data helps improve the semantic alignment between the input scene and the predicted environment map.
Semantic alignment.
Meaning the content of the predicted light map matches the content of the input image. This is vital. Without this, a model trained purely on synthetic data could hallucinate lighting based on dataset priors.
Ah, okay, so you feed it an image of a city street.
And it might give you back an environment map depicting a quiet rural landscape just because it picked up on patterns from its synthetic training data that didn't quite match the real-world context of your input image. This real data helps ground it.
Got it. Keeps it relevant. And the third source?
And third, LDR panorama videos. These come from datasets like WEB360. Now, even though they don't have that perfect ground truth HDR data.
LDR meaning low dynamic range standard video.
Exactly, standard video. But they expose the model to the richness of natural image statistics, real-world motion patterns, and diverse lighting conditions you see every day. This significantly improves robustness and temporal consistency, especially for video inputs. It helps the light flow and change naturally with the scene.
So the data strategy sounds incredibly robust. Synthetic for physics, real HDR for semantics, and real LDR video for realism and motion.
You've got it. A three-pronged approach.
But how does LuxDiT actually stitch all that information together?
Yeah.
Is there a particular training philosophy or approach that makes it all click effectively? How do you balance, say, the precision of synthetic data with the methy reality of real-world videos?
Excellent question. And that's where their clever two-stage training strategy comes in.
2 stages, okay?
The first stage is synthetic supervised training. Here, the model learns those fundamental physics-based image to HDR lighting relationships from that perfect synthetic data. This is where it builds its core understanding of how light behaves in a physically accurate way.
Building the foundation.
Precisely. Then, in stage 2, semantic adaptation, the model is fine-tuned using a special trick called low-rank adaptation, or LoRA.
LoRA, I've heard of that.
Yeah, it's a very efficient technique. It's used on those real-world HDR panoramas and LDR panoramic videos. Imagine you've spent years training a brilliant concert pianist. The whole orchestra is there. The fundamentals are perfect.
Yeah.
Now, you need them to learn a few new, subtle pieces in a specific style. Instead of completely retraining the entire pianist from scratch, LoRA lets you efficiently fine-tune just those specific parts that need adapting.
Ah, so it's parameter-efficient fine-tuning.
Exactly. It adapts the model to the nuances of real-world distributions, improving that semantic alignment we talked about, preventing overfitting, all while preserving that amazing foundational learning from the synthetic data.
That's a fantastic analogy for LoRa. Really helps make it click.
And what's fascinating here is that LoRa doesn't just make the results better. It makes them semantically consistent and believable for the input scene.
And the results speak for themselves, right? Not just visually impressive, but quantitatively superior.
Absolutely. LuxDiT significantly reduces lighting estimation error. You mentioned the numbers like a 45% reduction on Laval outdoor sunlight direction errors compared to prior methods. That's a huge leap in accuracy.
Yeah, that's substantial.
And it translates directly into quality. Qualitatively, LuxDiT produces remarkably accurate lighting with realistic angular high-frequency details.
Of sharp details.
Yes, which is a significant improvement over older methods that would often lose fine details. Think of crisp shadows or sharp reflections or yield distorted panoramas, especially with complex light sources or challenging scenes. It truly captures the character of the light.
Okay, so let's talk about the real-world applications where this character really matters. First up, video lighting estimation. Why is LuxDiT so much better here, especially for something dynamic like video?
Well, with video, consistency is absolutely everything, right? If the lighting jitters or flickers frame to frame, it completely breaks the illusion.
Instantly noticeable.
Totally. LuxDiT achieves higher accuracy and, crucially, significantly lower temporal variance in video inputs compared to just processing frame by frame or using other methods. This means smooth, consistent lighting transitions without any flickering.
Which is vital for...
It's absolutely vital for dynamic augmented reality experiences, where virtual objects need to react to real-world movement and light seamlessly, and for professional video effects that need to look truly integrated.
And I guess for many of our listeners, the most tangible impact might be virtual object insertion. Putting something digital into a real scene. Why is accurately estimated lighting so critical here? And how does LuxDiT make it so much better?
Yeah, this is where it really hits home for many people. If we connect this to the bigger picture, accurately estimated lighting is the secret sauce for making virtual objects look truly integrated and present in a real scene.
Present, I like that.
Yeah, we're talking about realistic shadows that actually match the environment, accurate reflections on surfaces, consistent illumination that makes the virtual object feel like it belongs there.
And LuxDiT nails this.
It excels at this precisely because it provides such a rich and accurate understanding of the real-world lighting. User studies have shown LuxDiT achieving a high preference. I think you mentioned the number, 60.6% over diffusion light for its realistic composite renderings.
Wow.
And it's even competing favorably with models that were specialized only for object insertion.
That's impressive.
What this capability really means is that the virtual objects you see in AR, in games, or in films can now react to light in a way that is virtually indistinguishable from real objects. It creates truly seamless experiences.
So no more floating, oddly lit digital items that just look wrong.
Exactly. It feels grounded.
That's incredible, going from potentially hallucinating a rural landscape or an urban street to perfectly integrating a virtual object so it feels truly there. But, even with such advancements, there are always areas for future growth. What are the current practical limitations of LuxDiT as it stands today?
That's an important question for any new tech. While LuxDiT is incredibly powerful, inference, that's the process of actually generating the lighting map, it remains computationally intensive.
Meaning it takes time and processing power.
Right. Due to the iterative nature of diffusion models, this can limit its use in truly real-time applications without further optimization. Though the pace of innovation in this area is rapid, so that could change.
Okay, so speed is one factor. Anything else?
Additionally, the resolution of predicted panoramas is currently limited by available data and the scale of training. It's excellent, but maybe not yet at the ultra-high resolutions needed for, say, highly immersive, super high-fidelity applications where every single pixel of light detail counts.
Got it. So computation and resolution are areas for improvement. So if those are the current practical considerations, what does the future hold for this technology? Where do you see it going next?
Well, future work will definitely explore techniques like model distillation or developing more efficient architectures to accelerate that inference step, make it faster and more accessible.
Right, speed things up.
Generating higher resolution outputs will also be key for truly immersive experiences in VR or high-end film production.
And longer term.
Longer term, we're probably looking towards unified inverse and forward rendering frameworks.
Okay, what does that mean?
Essentially, models that can jointly understand and predict lighting, geometry, and materials all at once from the input.
Wow, a complete scene understanding.
Exactly. This would lead to even more general-purpose scene reconstruction, where you could essentially digitize an entire environment's properties from just a single image or video. The potential there is huge.
That really opens up possibilities.
It does, but it also raises a fascinating point about the broader implications of such powerful generative AI.
The flip side.
Well, yeah. While LuxDiT enables these incredible creative possibilities, hyper-realistic AR/VR, stunning visual effects, generating pristine synthetic data for robotics,
Yeah.
it also brings a natural consideration the potential for misuse. Such highly convincing visuals could, in the wrong hands, facilitate the creation of deceptive content or manipulated imagery. Deepfakes, but for environments and lighting.
Right. That's always the concern with powerful generative tools.
It is. It's just a reminder that as these tools become more powerful, the conversation around responsible use and critically evaluating the digital media we consume becomes even more crucial.
A very important point. What a journey, though. LuxDiT represents a truly monumental achievement in tackling this complex, long-standing challenge of lighting estimation. By blending large-scale synthetic training with ingenious real-world adaptation through LoRA, it delivers unprecedented realism in digital illumination. It's pushing the boundaries of what's possible in computer vision and graphics, really helping us bridge the digital and physical worlds.
It's genuinely exciting progress in the field.
So let's leave our listeners with this thought. Imagine a future where any image or video you capture becomes a direct window into its exact lighting conditions, allowing you to instantly insert, remove, or change objects with perfect photorealism. How might this transform digital content creation, personal storytelling, and even how we understand and manipulate our own visual realities? Thank you for joining us on this deep dive.